Hello everybody, this is 2019 Poland Math Olympiad and here we go. This is a geometry problem obviously. I also have a sketch, so let's just try to make sure all the points are clearly marked, labeled on my picture, and we can move forward. So denote by capital omega the circumcircle. So this one is capital omega of the acute triangle ABC. Point D is the midpoint of arc BC. Okay, so if you, so the point D is clearly marked as the midpoint of arc BC on that cyclic, on that triangle ABC. So D is the midpoint of minor arc BC, okay? Not containing A. Circle lowercase omega, center that D is tangent to the segment BC at the point E. So basically we have that dark blue circle, so which is lowercase omega here. You guys see that? So capital omega is the circumcircle of triangle ABC versus lowercase omega is the circle centered at the point D, which is tangent to BC at E. And yeah, this is such a circle here. All right. What else do we have? Tangents to the circle omega passing lowercase omega, the small circle, passing through A intersect BC at K and L such that the points B, K, L, C lie on a line in that order. So basically from the point A here, we draw tangents to that little omega, the dark blue circle omega, and it would have two tangents at F and G, as you guys can clearly see in the picture. All right, so that's also makes sense. But furthermore, those two rays, AF and AG, they hit BC respectively at L and K as well. Do you guys see that? So B, K, L, C are 4 points in that order. Okay. And lastly, circle, we have two more circles, this purple circle and the green circle. Gamma 1 is tangent to the segment AL and BL and to the circle capital omega at the point M. AL, BL, and let's see, so capital M here. So there's a tangency here, yes. AL is this ray over here. BL is the same as BC. Do you guys see that they are describing the mixed linear, the L mixed linear circle of triangle ABL? Do you guys see that? The green circle. That's exactly the description of the green circle. All right, let me have the picture over there. And similarly, so this one is gamma 1 then. So this one is gamma 1. In the same way, so this is gamma 2, it turns out, I guess, right? Gamma 2 is tangent to AK, CK. Remember, K is this point. AK, CK, and the circumcircle at the point N. All right, so that makes sense. So that's gamma 2. Now the claim is that that's what we need to prove. Kn and Lm, knowing that they intersect at the point P, those two red segments, prove that Kap and Eal, they measure the same angle. So this green angle and the red angle, they measure the same. One thing, I think there's a little bit of the way the question is, in my drawing, it seems a little bit confusing here. That green circle, the mixed linear in circle over there, it's tangent at that green point. All right, it's tangent over here, and over here. Does that make sense? So the tangencies for the gamma 2 would be this point, and then these two purple points, so which is different than K and L. Do you guys agree? So the green point, so the tangency point is not K, it's that green point over here. And if you want, I can just even label those points, just if you want. So the tangency point, what can we call? Let's call it X, Y. I'm just labeling, and not that I'm gonna use it, but so that it doesn't you don't mix it up with K and L. X, Y, Z, and W. All right, they will have no bearing on the question, just to make sure the points are different. X and K are different points. Y and L are different points. All right, the tangency points are X and Y. K and L happen to be just the ray AG and AF meeting with BC. Yeah, I hope that's clear. All right, so with that said, the question wants us to show that these two angles on top, so KAP and LAP AE, those two angles being congruent. There's a couple of things, I guess, just immediately you can observe relating to the configuration of the picture. And if you want, this might be the right moment to pause the video. But try to list as many observations as you can, because there's quite a lot of things going on in this picture, okay, before even doing any construction of our own. So try to list as many observations as you can. All right, so if I'm assuming you guys have already paused the video, so let's begin. So first, there's this point D here. What is the relationship? Well, like D is the midpoint of arc BC, we are told, and that's how we were able to draw this dark blue circle omega, lowercase omega. Do you guys see that because D is the midpoint of minor arc BC, it must be on the angle bisector AI, right? Because angle bisector AI bisects angle BAC. So as a result, it will also bisect the arc opposite it. So does that make sense? So the first observation we have is that AID collinear, right? So I think that makes sense. All right, there you go. So AID is collinear. All right, what else do we have? I think a second one, this one is slightly more tricky, but simply by the fact that F and G are tangent. Now, we established that AID is collinear, right? So I hate doing this, but so suppose that I'm just going to erase this line because I don't think it's that useful, but just for the record, do you guys agree that because F and G are tangent at that point, so these two angles, they measured exactly the same? Do you guys agree? The reason is because AI goes through the center of our circle. It's this segment is the diameter of that circle, starting from here all the way up to here. So in a sense, if you want, let me draw the picture like this. Oops. So we have a circle, whoops, and we have, okay, so this is the center, D, and we have the two tangency points, F and G. Do you guys agree? So this is A, but it's clearly because this is an angle bisector. I mean, it has to be an angle bisector, sorry for that. It has to be an angle bisector because of, like, I mean, we have two congruent triangles here. This is a right angle, this is a right angle. So therefore, these are the radii. I think it's clear that triangle AFD and AGD are congruent triangles. So as a result, those two angles must be congruent as well. Does that make sense? Yeah, I hope it does, because then life is extremely simple then. Okay, so our second observation then was that GAD, angle GAD, is congruent to angle FAD, but if that's true, that would also imply, because BAD and CAD are also equal, do you guys agree? BAD and CAD are also equal, right? That means that BAG and CAF are also equal, right? BAG, or you can call it BAK if you want. Okay, let's call it BAK, I guess, is congruent to CAL as well. Holy. Do you guys see that? Wait. Yes, that's definitely true. All right, so what that means is because these two pieces are also already, BAG and CA, or BAK and CAL are already congruent. In a sense, what the problem is asking us is to show that this whole angle is congruent to this whole angle. Does that make sense? That's what the question is asking. All right, so let me change the color of the first one so that we didn't prove this yet, but that's what the question is asking, like in this. So as a result, therefore, it's clear that the question equivalently, so saying that the question was asking to show, okay, let me say it here, show, the question was asking us to show KAP angle, KAP is congruent to angle LA, sorry, what am I saying? Yeah, LAE, but clearly Now, alternative, we can instead prove the following. BAP is equal to CAE is equal to CAE. Now, what does that mean? Showing that BAP is equal to CAE. All right, so that might be okay, so what is the significance of E? We didn't talk about E yet. How about E? What is E? Is it in your list of observations? E is clearly the midpoint of BC, right? BE is equal to CE, implying that AE is a median. AE is median. So what it means is really, okay, so right now the question statement, we changed it to here, but now really what the real question statement is, if AE is a median, the question saying prove that CAE is equal to BAP is the same thing as, so this statement is the same as what? Showing that, so alternatively show that AP is a Symmedian line, is Symmedian. That's what the question is asking after all. Does that make sense? So Symmedian is the reflection of the median across the angle bisector. Does that make sense? So that's what the question is, because indeed, so based on it, just follow the angle chase, and I think that would be clear. That's it. But wait a second, what is the definition? How do we construct, or not definition really, but because definition is there. Definition of the Symmedian, like the name suggests, it is symmetric across the angle bisector, the median. If you take the reflection of the median across the angle bisector, you will get the Symmedian line. But how about the construction? So the construction, as you all know, is based on the following. You draw tangents at C and D. I mean C and B, I should say. And they will meet somewhere. And that's it. So our goal is to show that whatever that point is, let's call it Q, for instance, show that A, P, Q are collinear then that's what the question is actually asking. Does that make sense? Yeah, I hope it does. All right, so with this new formulation, I think already you guys are, you're already having a couple of claims in your head right now, right? What is the very first claim that comes to mind? Right after we did draw the construction for the Symmedian, like the tangents at B and C, you start looking at that point Q, and we were suspicious with the relationship between those two tangents and that blue circle omega, right? I hope that's what you guys are thinking right now. You are asking yourself, what if? Could it be? Well, especially if you are using a nice like a ruler and all the tools, a compass and so on. I think in your picture it must be clear that, yeah, so the claim must come out directly from there. So the claim is, you're probably thinking, could it be that blue circle omega is in circle of triangle BCQ, BQC. Could it be that? So yeah, I tried to kind of answer. Wow, so that would be perfect. So let me just get rid of this. So really, wait, can it be? But why would that be so? Okay, let me redraw, because we're just right now what do you call it? Speculating. Could it be the situation something like this? And it's not too difficult to see that, in fact, that's the case. Q. And you guys might be surprised, but we are going to use fact 5, the Incenter, Excenter lemma. But we're going to use the other direction of the Incenter, Excenter lemma. In the case of Incenter, Excenter lemma, we identify the Incenter, and then we say that BIC, the circumcircle of BI and C, the 3 points, is what? Has a center at the midpoint of minor arc BC. Here we start with the circle. Okay, so check this out. Consider, okay, so it will be a little bit, what do you call it? You need to really convince yourself that's the case. So pretend for a minute, I don't know if there's a tangency yet. We don't know yet. But think about it. Consider this triangle BCQ. Now, Do you guys agree that we have this point O, which is the circumcenter of the big circumcircle of ABC, and clearly because there's a tangent at B, that's a 90-degree angle, and then there's a tangent at C, that's a 90-degree angle. So that would suggest that BOCQ is cyclic, right? So BOCQ is cyclic. So we have this circumcircle of BCQ of our triangle. Now, the point O is such that OB is equal to OC because O is the circumcenter of ABC. But moreover, it's also equal to OD. Do you guys agree? So those three segments are equal. So therefore, because they are equal, the only explanation is because this is also the midpoint of minor arc BC. But remember, we are thinking about the triangle BCQ. All right. On this yellow triangle, O is the midpoint of the minor arc. So because those three segments are equal, it must be that D, the point D, is the incenter, the incenter of the yellow triangle. Now, this is the incenter, but secondly, it is such that the incenter is tangent at point E. And so as a result, do you guys agree that, the circle omega, I should say, the circle omega has also a center at D, and it is tangent to one of the sides of that yellow triangle. So therefore, it must be tangent to the other two sides as well. Does that make sense? I hope it does. So claim is proven as a result. Claim, check. Wow, so we did use the incenter, excenter lemma the other way around, like the converse of it, right? So the converse is also true. It's an if and only if statement. Nice. All right, so I'm gonna just get rid of this horrible looking blue circle. But yeah, I hope that makes sense. It will probably take a little bit of convincing. So like you can pause the video if you want to, I guess, right? But yeah, so that was good. So now we know that this is actually, so we claimed it and we proved it of this BQC. The only thing left is to show then, like we said, that this thing. Why is it then the AP is the Symmedian? Meaning, why is it that APQ are collinear? Alternatively, show. We keep writing alternative reformulations of the same problem. APQ collinear, right? That's pretty good. So I guess the key to finishing the proof is to discover what is special about the point P. Right now, the way we defined it, it is in the intersection of ML and KN on those two red segments. That's where the point P is. But we need to make more sense of that point P, all right? And when you look at it, it turns out that it is so the way we constructed the P is intimately linked to the way those mixed linear incircles touch the circumcircle, right? That gives us an idea of implementing Monge's theorem. Because yeah, so the point P actually is turns out to be a very significant point in that regard. Let me just remind you of Mangia's theorem. Let me just go down below. Just a quick reminder. So if you start with three circles, circle 1, circle 2, and say circle 3, for instance, all you do is you draw the pairwise tangents. So this point here, so suppose that this is the center of circle 1, that's the center of circle 2. So this is what we call as the X-simile center between those two circles. What it means is it is the center of homotety with a positive ratio between those two circles. There's also a center of homotety with negative ratios, and if you're wondering where that is, that's if you were to take the internal tangents. So there would have been tangency points over here. So this one point is what we call as an insimile center between those two circles, where the similarity ratio is negative. And you guys can easily check what that ratio is. So in that case, sorry for that, not that one. For instance, if you are checking the in-simili-center ratio, all you do is you just drop those two perpendiculars, which are parallel to each other. And because those points are collinear, they are also collinear with the x-simili-center, by the way. So you will see that there are two similar triangles, right? So this triangle is similar to that tiny triangle. And from there, you can find the ratios. And yeah, so that should be straightforward. But we're not going to use the in-simili-center today. We're just going to focus on the x-simili-center, so it's even better. So, oh gosh. All right, so I don't need any of this. And okay, so the in-simili-center and the x-simili-center, by the way, they are both on the line connecting the centers of those circles. So, whoops. So that's where the centers are. So this is O2, and this one is also perpendicular here. Do you guys agree that if the radius here is R1 and the radius here is R2, so we have EX12 is the center of homotheity with a positive ratio of R2 to R1, right? So, or if you are going from O2 to O1. All right, so similarly, you can just go ahead and figure out where are the remaining two x-simili-centers. I'm going to draw two more, so that's the second one. So this center is O3. It's obviously like previously, you know what, let's just change the color of this one because everything is blue is, okay, so this one, these two are also collinear. The centers of the circles and the x-simili-center, right? So this is EX31, 32 I should say, or 23, let's write it as. And finally, we need to check for the x-simili-center of, okay, so what are these brown tangency points? They still remain from what we did earlier. All right, so, and then you guys can also identify the x-simili-center between O1 and O3, which will probably go beyond where this is, but these two lines, they will intersect. Okay, I don't want to go down below, but or maybe I should. Okay, I don't even think it's gonna fit my screen, so pretend it's somewhere here. So this is EX, so it is between 3 and 1, circles 3 and 1. The claim is that those 3 points, and it's obviously also on that line as well, right? Because it's a center of homotheity. Okay, there you go. So this line also meets at that same point. The Mangia's theorem claims that those three x-simili-centers, they are collinear. So this one also goes to that point. Now, this is a very powerful result. The three x-simili-centers collinear. The proof follows directly from Menelau's theorem, and you guys can easily check that as well. So it turns out we can apply Monge's theorem in this construction to interpret the point P. So if you want to pause the video right now, try to find three circles that is somewhat related to the point P and see if you can figure what the point P is. All right, so I'm assuming you guys paused the video and let's check it out. So notice that we have let's start with, let's say, the purple circle. Gamma 2. So gamma 2 and the circumcircle are tangent at n. So therefore, it must be that n is the x-simili-center between those two circles. N is x-simili-center, simili-center of those two circles, capital omega and gamma 2. All right. But then secondly, okay, so this one is the following. If you focus on the in circle of triangle AKL, so this circle over here, let's call this circle as gamma. All right. So do you guys agree that K is what? X-simili center of gamma, which is the in-center of AKL, and gamma and what? Gamma and the purple circle, gamma 2. Do you guys agree? That's powerful. Okay, so this is the gamma, right? The blue one. And finally, okay, so how can we now combine this with Mangia's theorem? So by Mangia's theorem, so making these two observations, Mangia's theorem implies that the x-simili-center, x-simili of the remaining pair, namely capital omega and gamma, must be must be on where? On the line Kn. Do you guys agree? It has to be on the line containing those 2 points K and N. Must be on Kn. But by a similar argument, we can notice that M is the x-simile center between capital omega, our circumcircle, and gamma 1. Similarly, L is the x-simile center between the green circle gamma 1 and gamma. So therefore, it must be that the x-simile center between gamma, the incircle of KAL, triangle KAL, and the circumcircle of ABC, it has to be on ML as well. Analogously, x-simile center of omega, capital omega, and gamma must be on where? On ML as well. ML as well. So the x-simile center of those two circles, the circumcircle of ABC and the circumcircle of AKL must be on KN. The circumcircle of ABC and the circumcircle of KL must also be on ML. There's only one point which satisfies both conditions, right? And it is the point P. Oh my goodness. So P is the x-simile center of these two circles. But how can it be? Remember earlier when I did draw the picture was like this. Well, it turns out that when I did draw the picture the way I did here, the two circles were not intersecting, and one of them was outside the other one. When that's the case, identifying the x-simile center is direct by using the tangents. Finding the center of homotety is easy. Finding the center of homotety when the two circles are inside each other is slightly different, and now we have actually figured that P must be the center of homotety between those two circles. This reminds me of the, if you want to have an exercise, try to find the x-simile center between the 9-point circle and the circumcircle of a triangle ABC. So that's good exercise. Both the x-simile center and the in-simile center. Can you find a center of homotety for circles which are not outside each other? Because when they are outside each other, they are not intersecting, overlapping, or intersecting with each other. Life is pretty easy. Most people, they just draw the tangents. But yeah. Okay, anyhow. But now P is a point which is significant, right? Wow. So P didn't know it was Hercules. It turned out to be an extremely significant point. P is the, again, let's repeat, the x-simile center between those two circles, the circumcircle of ABC and the incircle of KAL. Wow. Okay, but now we can wrap up our argument. Remember, our goal was to show that A, P, and Q are collinear. We might as well invoke Mange's theorem one more time. All right, this time we're gonna get involved the circle omega, right? The lowercase omega, I should say. This time, let's apply Mange's theorem using, again, our circumcircle, this new circle that we invented, the gamma circle, the incircle of AKL, and now this other circle, the incircle, which we proved, incircle of BCQ. All right, so if we apply Mange's theorem, first of all, we already established that P, let's make notes next to it, So P, this one is the x-simile center of what? Of omega, capital omega, and gamma. I think that's clear. Now, the point A, how about the point, actually Q is easier. Q, the point Q, how about Q? Well, it's obvious, right? Because there are tangencies at C and B, but there's also tangencies here and here as well. Q must be the x-simile center of what? Of the circumcircle and omega. Do you guys agree? But now, let's have a look, one more look. How about the point A? Now, when you look at it, wow, this is amazing. Notice that there are tangencies at G and F, but because this is the incircle, omega is the incircle of AKL, do you guys agree that those tangencies, they meet at A? Wow, so the tangencies, I can call them as F, G, H, K. So you can call this one as H and, well, we already, H1 and H2. Do you guys agree? So there's a tangency at H1 and H2 for gamma, and G and F for omega. They meet at A. So this is the X simili-center between gamma and omega. Wow, 3 X simili-centers for 3 pairwise circles. These 3 points must be collinear by Monge's theorem again. And that proves the result. All right, so I'm going to leave a link for the AOPS page for this question, and you guys can see different solutions. Almost in all of them you use variation of Mangia's theorem. You could have done we could have avoided using the Symmedian line argument and completely finished the problem by simply using, I think, 4 or 5 repeated applications of Mangia's theorem, but I think we already used it several times already. So but combining it with the idea of Symmedian, I felt like it is more natural for this question, as well as making use of an argument of Incenter, Excenter, Lemma, though the converse statement. I hope you guys enjoyed it. And that's it. No more question during spring break. So have fun, and looking forward to see you guys probably a couple weeks later. All right. Bye, guys.